All right, in this video, we're going to take a look at graphing some polar equations, and we're going to comment on the graphs as well. So example 2a, we've actually seen this before in our polar coordinates video, but we have r equals 6 times cosine of theta. Now, what I'm going to do is I'm actually going to trace this out for values of theta between 0 and 2 pi in multiples of pi over 8 radians. So here I have example 2a, 6 cosine theta, and I'm going to have theta range from 0 to this value of q, which is going to range from 0 to 2 pi. For more information on this, I do have a video tutorial on how I did this in my Desmos playlist. But as we adjust the value of this q sub 1 here, it's going to trace out the graph of 6 cosine theta, which we've seen the equation before. So tracing it out, and notice it took pi radians to get one full circle. Now if we continue to go, it's just going to retrace along the same graph. So really not much change there. We only need pi radians to trace out the entire graph. But with r equals 6 cosine theta, notice it is a circle. The center's at 3, 0. The radius is 3, which makes the diameter 6. In fact, this number out in front, this 6, tells you what the diameter is. Now, because it's cosine, it's going to go along the x-axis, or the polar axis here. If we made this negative 6, it would reflect it so it's on the negative side. And because it's cosine, it's flipping over, so it's left or right. If we change from cosine to sine, it's going to make it either up or down. So negative 6 sine theta would make it facing downward. Again, notice that the circle's diameter is still 6. That has not changed. So with 6 cosine theta, it is a circle. The center's at 3, 0, and the diameter is at 6. It also goes through the pole or the origin. So, all right, part B, r equals 4 minus 2 sine theta. So let's clear out this graph here. And part B, we have 4 minus 2 sine theta. And again, I'm going to trace this graph out and see what it looks like. So this is pi over 8. So if you want to fine tune it, you can set it to be pi over 12 or whatever you like. So adjusting this value, keep going. And okay. So it appears to be circle-like, but it's like a circle that's been pressed downward from the top. Notice we have a sign here, which is causing our circle to kind of be more focused in the vertical direction than the horizontal. If we change it to cosine, we would see it's more focused in the horizontal than the vertical. So here we have 2 for our radius going up, and we have negative 6 for our radius going down, which we could adjust the value of 4 and 2 here and see that there actually is a relationship between this smaller part from the pole or the origin and this larger part as well. So think of how you can get this 2 from a 4 and a 2. Think of how you can get this 6 from a 4 and a 2 as well. Also of note that we have at negative 4, 0 and positive 4, 0, which just so happens to match with this 4 here. So 4 to the left, and 4 to the right. So as far as the analytics of this graph, it's called a limaçon, which I believe is the French word for snail, because I guess it does resemble a snail. The x-intercepts, again, at plus or minus 4, 0, as we saw. And our y-intercepts are at 0, 2, and 0, negative 6. So in Desmos, you can adjust the values for here, for 4 and 2, and see how that affects your y-intercepts. All right, part C, we have 2 plus 4 cosine theta. So let's get rid of this. And example C, we're going to do 2 plus 4 cosine theta. So let's trace this one out. So tracing it out. And this one's starting to, at pi radians, we've kind of got it to almost spiral in on itself. Let's see what happens. So we're looping. Okay. And there we go. We get this interesting looking graph. So it's almost like the last one where we had a circle and we pressed inward on it. This time it looks like we're pressing inward to the point where we're forming a loop inside of our circle, for lack of a better term. So let's see, we have it at it does intersect the pole or the origin. This time we have y-intercepts at 0, -2, and 0, +2, which might have something to do with this 2 over here. And our inner loop, our inner loop has a diameter of 2, and this outer loop here, this outer part here, goes out to 6. So again, think of what we can do with the 4 and the 2 to get this inner loop of 2. Think of what we can do with the 4 and the 2 to get this outer diameter here of 6. So this graph here is also called a limacon. In this case, we have an inner loop. We pressed inward a little bit more than we did in the last one. Our x-intercepts are at 0, 0, the pole, the origin, 2, 0, and 6, 0. And our y-intercepts are at 0, ±2. Our inner loop diameter, as we saw, was 2, and our outer loop diameter, as we saw, was 6. So, again, notice that we had 2 plus 4 cosine theta here, and for this one, we have 4 minus 2 sine theta. So look at the relationship between the number in front of the trig function and the constant. Also, this one for cosine going left and right, just like x goes left and right. The one for sine was more up and down. So again, the cosine versus sine, is it wider left and right? That's your cosine. Or is it wider up and down? That's your sine. All right, part D, we have 5 times the sine of 2 theta. So let's take a look at what that graph's going to look like. So 5 sine 2 theta, we're going to trace it out. So we got a loop, got another loop, got a third loop, and we got a fourth loop. So what we have here looks to be like a butterfly or a flower. The diameter of each of these loops is 5, which just so happens to match this value right here. And we have a total of 4 petals. Well, let's see what happens if we make it 5 sine 3 theta. We get 3 petals. 5 sine 4 theta, we get 8 petals. 5 sine 5 theta, we get 5 petals. So it appeared as if the number of petals is dependent on the value in front of theta. If it's an odd number, it's going to equal that number of petals. And if it's an even number, it's going to be twice that many petals. Let's see what happens when we change this to cosine. So cosine. So cosine, we can go 2, 3, 4, 5. Notice each time that we're going to have a petal for cosine along the positive x-axis. If our value in front of theta is odd, we will not have one on the negative x-axis. So there's 5 theta. But if it's even, we will have one on the negative x-axis. So with cosine, it's always going to have one on the positive x-axis, and then depending on whether or not the number in front of theta is odd or even, we'll also have one on the negative x-axis. Again, notice the 4, we have a total of 8 petals. So this family of curves are called rose curves. Even, maybe that's more of a daisy like to me. I don't know, I'm not a botanist. Our radius is 5, so the larger this number out in front, the larger our rose curve will be. This one has 4 petals, and again, as we saw, this one has no petals on an axis, but if it was cosine, it would. And we also notice the number in front of theta. If it's even, we double that number to get the number of petals. If it's odd, it's equal to that number to get the number of petals. All right, finally, part E, we have r squared equals 16 times the cosine of 2 theta. Here, we unfortunately, as of this filming of this video, Desmos does not allow you to type this in directly. So you actually have to solve for r. So take the square root of both sides, and you get plus or minus 4 times the square root of the cosine of 2 theta. So the good news is 4 square root cosine 2 theta and negative 4 square root cosine 2 theta, they should produce the exact same curve. So just to show that, here we have 4 cosine theta. Well, let's trace this out first. So we got more loops. And we get an infinity symbol. Now if we make this negative 4 cosine theta, it doesn't change anything. I'm going to leave it to you to figure out what will happen if we change this from cosine to sine. So kind of use your intuition there. But we get this infinity symbol here that we've seen quite a bit of in this class. So that infinity symbol is known as a lemniscate, and I might be butchering that pronunciation. Our x-intercepts are at 0, 0, so it does go through the pole or the origin, and at plus or minus 4, 0, so we go 4 units each way. Our y-intercept is at the origin or the pole, and that's about it. So again, for these ones, we have to get r by itself before Desmos will allow us to graph that. So, all right, that about does it for this video. Thanks for watching. I'll see you next time.